picking up where we left off in 6.3. We are ready for example 4, yes? I filled in bits and pieces of example 3 that I think will be helpful to example 4. If there's anything else we need to fill in, you have it in front of you, so I probably just should have filled it all in, to be honest, but that's all right. So, example 3, review, because example 4 is based on example 3. Example 3 was the integral of f of t dt from 0 to x, okay? Now, we're going to consider this function, and it's the integral of f of t dt, but from 3 to x, okay? We're not going to go through and do an xy chart like we did everything else, okay? We're going to more relate our, when I say g of x values here, to f of x. So I am going to start off with our first value by plugging in 0. So if we plug in 0, g of 0, what's that say to do? That says to do the integral from 3 to 0 of f of t dt, yes? Now, 3 to 0. What's wrong with that?
Don't matter.
Okay. Normally, what do we normally see? The smaller number on bottom, bigger number on top. This is reversed, okay? And the idea here, so if we're going from 3 to 0, I don't know exactly how you want to look at it, but that would be going backwards in a way. There is a property or a rule that says if you can take, if you have these numbers are upside down from what you need, you can take them and flip them. But when you take them and flip them, it changes the integral to a negative. Okay? And that's the idea, I think, because you go from 3 to 0 instead of 0 to 3, it makes it negative. So what I'm saying here is that this integral from 3 to 0, and we'll learn more about this later, is equal to the negative of the integral from 0 to 3 of f of t dt. Now, I'm realizing probably it was not a great idea to split 3 and 4 from yesterday to today, but that's all right. We'll dig deep. We'll make it work. The negative of the integral from 0 to 3. What was the integral from 0 to 3 yesterday? $4.5? Yes?
Yeah.
The integral from 0 to 3, sorry, I'm not trying to make that a negative sign or anything, I was just trying to make a point there, is 4.5. I wrote it as 9/2, but 4.5. So the integral from 3 to 0 is negative 4.5. So what happened is now 0 matches up with 4.5, but it's going to be negative 4.5. So look at what happens if we go to graph this, because I guess it says sketch the graph of g in green. How can we even answer all these questions? I don't know. So when you plug in 0, we get negative 4.5, yes? You do you, whatever color you want, but that's what I always do. If I use something other than green, which I do sometimes in my notes, like, this is not green. Just saying. So I just highlight it there and say, okay, there's the color I used. So, oh, that's supposed to say equals negative 4.5. With that in mind, okay, let's see. We might sketch the graph now. We might sketch it later. We'll see. What is the 0 of g? No, other way around. So 0 is when it, in this case it was 0, because that's when it touches the x-axis, yes? Think ahead. When is this integral going to equal 0? When I put what x value in? Look at g here. When I put the x value of what in for x, does this integral equal 0? What'd you say? 3. Do you remember that? Because what happens when it's 3 to 3? When you're going from the interval 3 to 3, does any area occur? No. So it's automatically 0. So your 0, okay, when we put in x equals 3, is going to be at 0. Okay. We already did b. I guess maybe I wasn't supposed to do b already. What is g of 0? Negative 4.5. I already graphed that, yes. Okay. What is the domain of g?
Which is 0 to 10 again?
Yeah, it's going to be 0 to 10 because we're looking at this graph of f, and so it is going to be 0 to 10. So 0 less than or equal to x less than or equal to 10. Okay. D. What is the total change in g? Do you know how to answer that? I'm debating.
F is 0. Not F.
Well, okay, yeah. So based on what we did yesterday, we used what? Well, actually, yeah, it's not going to be f. It's going to be
G of 0.
g of 10 minus g of 0. Yes? Now, we haven't found g of 10. And I don't know if I want to take time to do that or if I want to take us a different way on this. That's where I was kind of debating. Let's kind of pause for a moment. What do you notice here? When we plugged in 0 last time on f, it was 0. When we plugged in 0 here, what did we get? Negative 4.5. The other value we already know. When we plugged in 3 yesterday, we got 4.5. When we plugged in 3 today, we got 0.
That changes 6.
Well, okay. Don't think total change. I don't think that's what.
I was just saying this, like,
Okay. Each of these points is down what? 4.5. What's going to be true of all the other points?
They're going to be down.
They're just going to be shifted down 4.5. So this dot that was at 1, 1/2, if I move that down 4.5, it's going to be at negative 4. This is why I'm like, sketch the graph. I feel like it's so much more helpful to sketch it earlier rather than later.
So then would the total change be 1.7?
It would be 6.
No. Total change is going to be
6 now.
6.
Why? Oh, because it's the same.
It's the same because my graph is going to have the same shape.
Oh.
It's just going to be shifted down 6 or down. It's going to be shifted down 4.5. The highest point and the lowest point are still going to have the same difference. Or that's not what I want to say. The end point and the beginning point, while shifted down 4.5, they're still going to have the same difference between them.
Okay.
That's what I'm trying to say. Sorry. Okay. Maximum value of G. Might be helpful to
7.5.
I think. And why 7.5?
It's 4.5 less than 20.
Okay. So earlier, yesterday my max was at 612. What's 4.5 less than that? 1, 2, 3, 4 and a half. So you're at 7.5 there. Where will it occur?
X equals 6.
Still at x equals 6. What is the range of G?
Negative 4.5.
Negative 4.5, less than or equal to y, less than or equal to 7.5. Okay. I am going to sketch the graph. I am going to put the rest of the dots on here. So let's see. We already did the dot at 1. The dot at 3 is already done. The dot at 4 was at 8. If I go down 4.5, I'm going to be at 3.5. The dot at 5 was at 11. Oh, wait. Yeah. The dot at 5 was at 11. So 1, 2, 3, 4, 6.5. Yep, 6.5. I already did my dot for 6. At 7, it was at 11.25.
So it should just be a 7.
How about 6.75?
Just
At 9, it is at 4.5. 9, 6.75. And I do agree with the 2.25. And 10 was at 6. Now it's going to be at 1.5. If you connect your dots, it should look like the same shape, yes?
Do any new colors today?
I don't know. I really don't. I don't really know. I don't see anything that's talking about colors.
Thank goodness.
Okay, so the rest of 4, technically 4 is not over, kind of sums it up. Describe the relationship between all f of x equals the integral from k to x of f of t dt as k takes on different values.
Will they all be? Never mind.
I was waiting to see where you're going to go with that.
Will they all be 4.5 away from each other? Or will they all always have?
They won't always be 4.5 away from each other.
Or they'll always have the difference of 6?
Well, on our particular problem, the total change would always be 6. But what's the relationship? Like this one, because we started at 3 instead of 0, it shifted down 4.5, right? What if this was the integral from 4 to x? Well, now it's going to shift 8. Okay. In other words, based on where it starts, they're all going to be vertical shifts of each other. Okay, so like this one, as I said, because it started at 3, it went down 4.5. This one, if it started at 8, or if we used 4 to x, the integral from 4 to x, it'd be shifted an increment of 8. Okay, so the point is, if it's referencing the same original problem, they're all going to be vertical shifts of each other. That's what we're looking for there. Okay, so just depending on what we have there. So I have all f of x are vertical shifts of each other. Okay. And J, when you're ready. What point must lie on the graph of any given family member?
The finger.
Huh?
Is it the finger?
Just a part where you just tell 0 from that over.
What'd you say?
A 0.
A 0. And when does that 0 occur? In other words, on,
Inverse.
The K and X are equal.
right, when k and x are equal? Because here it was at 0, 0, right? Here it was at 3 to 3. And so the idea when k and x are equal, so the point k, comma 0 will always lie in the graph, because k is what you'll plug in to where k and x are equal, and you'll get 0. Okay, very good. So what do I have for my explanation? When the lower bound equals k, yeah, basically my explanation. So when lower bound is k, the area is the integral from k to k of f of t dt. And the integral from k to k, what have we learned? Is 0. So you're plugging in k and getting 0 out. Okay. And then part k, not to be confused with the variable k. Give us a moment to finish writing before I...
Oh my god, you just stop yawning. Making me yawn.
As k takes on different values, the function f of x equals the integral from k to x of f of t dt, the function's graph, as what transformations of one another, each containing the particular point blank. This is based on what we've just said in our last couple of answers. What's happening to the different graphs? They are what kind of transformations of each other? Vertical, because they're moving up and down, right? So they are vertical transformations of each other, containing the particular point,
Okay.
not just k, but what's the ordered pair?
K0.
K0. When you plug in k, you're going to get out 0 because your upper and lower bounds will be the same. Even though the lower bound is changed, does f prime of x still equal f of t dt, or f of t? In other words, even though my boundaries are changing, does the derivative of capital F of x equal f of t? And yeah, it does, because remember we talked yesterday that when you take the derivative of an integral, they're going to cancel each other out, okay? And so, yes, it will. Okay. I think that takes care of example 4. As I said, had I realized breaking 3 and 4 up between yesterday and today was probably not the best idea, but
Oh, well.
it is what it is. Okay. 5 gets its own page. Shown below is the graph of the derivative of f of some function f. Derivative lowercase f of some function capital F. Assume f of negative 3 equals negative 8. Okay, so vocabulary-wise, when we say assume f of negative 3 equals negative 8, I am going to use the idea that that is an initial value. Okay. And notice, where is negative 3? Negative 3 is right here, yes? So keep in mind, f of negative 3 equals negative 8.
So what's the graph?
The graph? Okay. So the graph is f of x. But notice what it says is the graph is the derivative f of some function capital F. So it's the idea of what we've been doing where f of x is the integral. It's that idea. Okay. Or, yeah. Or actually here, would it be easier? The derivative? No, I don't want to say that. Would have been better to leave it the other way. Sorry. Okay. Give me a moment. It'll make more sense when we start going through it. Okay. So A is f of 2. What'd you say?
8.
No. I was trying to figure out how you even got that, but I don't know.
Because they're at the
0.
same point.
F of 2 is 0.
F negative
I'm
3
having
is
so
negative
fun.
8 and have the same point. It was a guess.
Okay. With them giving us this initial value, okay, they're saying right here that f of negative 3 equals negative 8. Anything you do to the right of this, any areas you find to the right of this, you're going to be, as we go right, we're going to add these on. Any areas we find to the left of it, we're going to be subtracting it because we're moving backwards from that value. Okay? So anytime we go to the right, we are accumulating those. Since this is at negative 8, at this point, then that means anything we go to the left, you're going to be taking away from that negative 8. Because what we know is at this point, at negative 3, the area is accumulated to be negative 8. Now, if we are going to f of 2, well, what's the starting value we can use? F of negative 3 is what? Negative 8. As we move to the right, they've already done the math for us. What do we know? Yeah, those numbers in the boxes are the areas.
Add 10 plus 28. 26.
28.
Add 10,
Plus 28.
add the 26, which you can kind of tell in mind that 26 represents that whole piece, right? She just has it over to the left there. It represents that whole red piece on mine. And then, does that take me to 2?
Mm-hmm.
That takes me to 2. So it is negative 8 plus 10 plus 26.
28.
Okay. Now, what about f of 6? What can I do there?
Add 14 and 8 to 26.
Subtract
8. Add 14.
That's
What?
6. Add 6 to 28.
Yeah.
You get 34.
So why are we needing to subtract the 8?
It's below.
Where is the 8? It's below the x-axis, so the area is negative 8. Or the area is 8. We think of it as a negative because it's below the x-axis. So, were you guys starting with 28, I take it?
Yeah.
Starting with 28 where we left off, subtract 8, add 14, puts us at 34. Or yes, the net change is 6. I'm with you there, Doug. But I had to get Kylie to see the negative 8 that she was not seeing for a moment. You don't like this game? Okay. F of negative 5.
Negative 8 minus 18.
Okay. So we know right here it's at negative 8. This is before the negative 8. So we're subtracting it off. Negative 8 minus 18 is
Negative 26.
negative 26. Okay. Since the area under F is positive on the interval from negative 3 to negative 1, we know that the graph of F must be blank on the interval from negative 3 to negative 1. No? Because it is positive, it's going to make F to be increasing. Because remember, little f is the derivative. A positive derivative tells us the original graph is increasing. Okay? Since the area under F accumulates at an increasing rate, we know that the graph of F must be blank on the interval negative 3 to negative 1.
Concave up. Good job.
Okay, so accumulates, the key here is we're talking area and it's increasing rate. Okay, because it accumulates at an increasing rate, that refers to concave up on the interval to -3 to -1. And realize we're getting ready to graph all this, aren't we? Okay, so the area under F on -1 to 2 accumulates at a blank rate, so F must be blank on the interval -1 to 2.
Decreasing rate.
So I know I that was my thing. I was trying to figure out like where are we at. So -1 to 2,
Decreasing.
decreasing rate. So capital F must be
Concave down.
concave down.
Hooray.
Okay, guys. Sketch a graph of F. Show extrema, inflection points, and horizontal tangents. Now, we have some information to fill in. We know all this information, or most of it. -5. What is F of -5?
-26.
F of -3.
8. -8.
That was given. F of -1.
10.
2.
2. Yeah, 2.
Do we know that, or are you guys figuring it out?
No, because it says under F, right?
Okay, so you're at -8, you add 10, you're at 2. All these others were like, most of these we've already done, haven't we?
No.
F of 2, we already did. F of 4, I think we have to figure out.
20.
Yeah. I looked at F of 6 as 34 and subtracted 14. Or you can look at F of 2 as 28 and subtract 8. And F of 6 is 34. Or we could have just redone all those, the whole, but.
Heaven forbid it be easy.
Okay. So, we are graphing F of X here. Okay, that's what it's asking to sketch a graph of. So, let's put our points in. You don't need me to put the points in. We'll talk about connecting them here in a moment. -5, -26, -3, -8, -1, 2, 228, 420, 634. Am I teaching seniors or middle schoolers here? Jeez.
Sorry.
Well, right now in middle school, they can't freaking eyes open.
Oh my god.
I'm falling asleep.
I watched
Oh my
the middle
god, I
school
did
today
this all wrong.
start snuggling.
How did you do this all wrong?
I did it for positives.
But there's some negatives involved.
I know.
Okay.
Did you guys all do that?
What did you guys
This one
do?
right.
We're just graphing ordered pairs, folks. I don't understand here.
It's hard.
Maybe you are. It's hard.
Okay.
Okay, there we go.
Then
Oh
we
my
can
God.
just connect them, right?
To an extent. Now, keep in mind, we talked about what? -3 to -1. The graph is going to be concave up. Yes?
Yes.
And so, easier said than done there. But, a little bit of a, facing that way. From -1 to 2, it's going to be more
Oh,
concave down.
Dang it.
Easier said than done. But you want a little bit of curve facing down. It's kind of a difficult area to work. But are you seeing the idea?
Sort of.
Let's see, if we go back to that first section, from -5 to -3.
So this is straight.
That would be,
Concave down.
I'm down.
yeah, it was a decreasing rate, so more concave down. And again, easier said than done on some of these, right? 2 to 4. Well, what do you have? You have decreasing, but then you have
Increase.
increasing. So is there kind of an inflection point there in the middle?
Sure.
So 3.
So the idea of concave down to concave up. And then this is increasing, so concave up. Ish. You know.
Drawing curves is my kryptonite. That's the one thing I cannot do very well.
That's a really cool looking graph.
It's a really
Okay. We talked about, and along the way, I mentioned an inflection point, yes. Any place we change from concave up to down or vice versa, it's an inflection point. Extrema. Extrema are your
Maybe max.
mins and maxes. We have some of those, right? I see a max, I see a min. Horizontal tangents. Where do horizontal tangents occur?
-3, -8.
0.
Yeah.
No.
It's
At mins and maxes.
At mins and maxes, yes. Horizontal tangent. Could occur right here.
Right there.
Could occur right there.
Yeah.
so what's a -3, -8?
Inflection point, maybe? Did our concavity change?
Yeah.
Our concavity changed, so that's a inflection point. That's not necessarily a horizontal tangent,
So
then.
then that's a min and a max because it's an inflection point,
So,
right?
not necessarily.
So a -1, 2 be an inflection point too.
Oh no, mins and maxes are inflection points.
No, mins and maxes are extrema, and
Oh, yeah,
horizontal
yeah, yeah.
tangents can
No, but
occur.
whenever it gets converted over to
When
the
it-
other.
When it changes concavity is when we have the inflection points. Okay.
But like if it goes like to F double or F prime or whatever
It's F prime.
prime we're in and
The-
whichever, if we do it
It becomes
because
0.
it's a graph.
I see. You're looking at, okay. I'm following where you're at now. It was taking me a moment to follow where you're at, so I'm there. Okay, now, and on that graph, it says show. I don't have anything labeled on mine, so we've talked about it. We're good.
Last page. Ready to go.
Okay, let's do it.
We have 4 more problems tonight.
Okay.
All 4 pages.
In differential calculus, so when we're talking all of our derivatives, we use the derivative f prime to discuss properties of a function f. In integral calculus, we need to reverse our thinking. Our new goal is to use derivative functions to talk about antiderivatives. An example below, we say that g is an antiderivative of f. Let's summarize the relationships between properties of a function and its antiderivative. Okay, so given this graph of f, okay, so notice it is a graph of f. Notice it says g of x equals the integral of f of t. So what this to me says is if I take the derivative of g, what happens when I take the derivative of an integral? They essentially cancel each other out and it's just going to equal a regular f. Okay, that's the connection my brain personally does better if I go to. Okay, so with this in mind, let's see. F is positive on the interval from 0 to 8. Okay, so what does that say about g on this interval?
That's positive.
Increasing? Okay, so again, we're reversing our train of thought, I guess you could say. Okay, so if f is positive and g prime is the derivative, then that means it's going to be increasing. F changes sign at,
X
Zero
equals
and
4.
I only have the 8 on here. Why? I don't know. But that's all that they have. So F changes sign at X equals 8. Fair enough? If we just talk about the X equals 8. So G must have a what?
Is it a max or a
max.
min?
It's a max because it goes from positive to negative.
Oh, yeah.
Okay. If it's going from positive to negative, that means it's going from increasing to decreasing. Does that make sense? So it is a relative maximum. I just answered this next part then. Since F goes from
Is it positive and negative?
positive to negative.
What?
Yeah. Pretty-
Ugh.
Because we're looking here at F, and F changes from positive to negative,
Oh, yeah.
which means the G would change from positive to negative. Or increasing, decreasing, sorry. Okay. The graph of G, not pictured, right? The graph of G is decreasing where F is negative. For values of what?
Well, you don't know what's happening before that.
Okay.
Did you say K?
Yeah, I'm just saying so.
Okay. Think in terms of values less than or greater than a certain number up here.
4 less than or greater than 0 less than or greater than 8.
Too many less than, too many less than greater than, too many numbers there. So the graph of G
Less than 0.
is decreasing where F is negative. And where is F negative?
Less than
X is less than 0. And X is greater than 8.
Okay, and since for whatever reason we appear, oh, I know why we're not using this, folks. Probably because this just starts at 0.
Zero.
Oh, that makes sense.
Okay,
F
so
greater than 8.
in that case, we're just referring to X greater than 8. So G is decreasing where F is negative, and F is negative for all values greater than 8. Are we there yet?
Yeah.
Sorry. I don't know why I made that one so difficult. My brain. Okay. The graph of F is increasing on,
0 to 4.
okay, so this is F. It is indeed increasing from 0 to 4. So 0 less than X less than 4. Do I want equal to's on those? I can. 0 less than or equal to X less than or equal to 4. Now, so if F is increasing, what is G doing? Yep, we're talking concavity. Concave up. The graph of G is concave down where F is decreasing.
X is greater than 4.
Yeah, X greater.
It's decreasing when X is greater than 4.
What
Okay.
equal to? Is it equal to, or is it just greater than?
Because at 4, it's neither increasing or decreasing because it's at max.
It's
So
just- okay.
and there's some wiggle room on sometimes whether you use equal to or not, there's wiggle room. Sometimes there's not, but. Okay, the graph of F has a max at
4.
X equals 4.
That'll be-
So G has an,
Actually,
Well, actually,
I'm using words.
you want to put inflection point because POI starts with a consonant and means that start with a vowel.
What?
So we should be saying an inflection point instead of an POI, point of inflection. Whatever.
My bad.
Yeah.
Okay.
Silly.
It's grammar.
Okay, that wasn't as bad as you guys thought it was going to be.
Yes, actually.
Okay, on the bottom here, you guys have seen these pieces, okay? The symbols are here again. We've used these symbols previously, but this is just kind of our connection chart, okay? When the derivative function is positive, the antiderivative is going to be increasing. When the derivative is negative, the antiderivative is going to be decreasing. When the derivative is increasing, antiderivative is concave up. When the derivative is decreasing, the antiderivative is concave down. When the derivative changes signs, the antiderivative has a extrema. I don't know why she throws in how do I say that?
Extremum.
Extrem? Extremum?
Extra mom.
Do we have an extremum in the room? Okay. So I'm going to go with extrema because that's the word we're used
Would
to
you like
saying.
some supper? Extra, Mom.
Oh my god.
Okay. On that note,
Awesome.
6.3.
Oh my gosh, we
Check
have
it
one
off.
more